Hello students. So in this lecture I will tell you the use of a chemoselective concept in disconnection approach. Okay, so what is this chemoselectivity? So chemoselectivity is the selection of one functional group in presence of other functional group, or to select one functional group for the reaction in presence of other functional group, that is called as the chemoselectivity. So if we define the chemoselectivity, that is, it is the selection of one functional group for reaction in presence of other. Means if you have two functional groups, it may be identical functional group, it may be different functional group, then we have to react only one functional group. So this can be done in a different way. So it can be done in different way. One of the way by using chemoselective reagent. So this chemoselective reagent, it selects only one functional group for the reaction. If we have two functional group, then it will select only one functional group. For example, suppose if we have a two functional group and both are suppose the same functional alcohol. Okay, suppose two alcohol groups are present, and if we react it with suppose any oxidizing agent, for example, if we react it by pyridinium chlorochromate, PCC, then both of the OH will get oxidized into carbonyl group. But if we react it with manganese oxide, MnO2, then only one OH group will get oxidized. And the OH group which is oxidized is the allylic OH. So this is your allylic OH. Allylic OH group that would be oxidized into carbonyl group, and this will remain unreacted. So this will remain unreacted. So MnO2 is the chemoselective reagent. So we have selected only this one for the reaction. Okay, this allylic OH is selected for the reaction, and this one remains unreacted. In the same way, suppose we have now one of the carbonyl group is present, another is this nitro group is present. Now if we do the reduction by using lithium aluminum hydride, then lithium aluminum hydride will reduce both of these functional group. Now if we use NaBH4 sodium borohydride, then only one functional group will get reacted, that is this carbonyl will get reacted, NO2 will remain unreacted. So what would be the product? This would be oxidized to alcohol, secondary alcohol, and this NO2 will remain unreacted. So this NaBH4 is the chemoselective reagent. Okay, so this is one of the way that we can, this chemoselectivity can be done. Another way, by protection, by protecting one functional group. So if we have two functional group, then we will protect one functional group and another functional group will get reacted. Okay, so this protection, or we can say we can do the masking also. Okay, one functional group is masked and another functional group will remain unreacted. Now third one we can do by taking limiting amount of reagent. Okay, by taking limiting amount of reagent, means only one equivalent of reagent is taken. Suppose if both of the functional group is to be reacted, then it will require two equivalent of reagent. Now if we take one equivalent of reagent, then only one functional group that can be reacted. But in presence of some, it needs some conditions that we will discuss in a coming time. Now next, by converting the starting material, or by converting the, we can say, by converting the reactant into its derivative. Okay, for example, so I will discuss it later. Suppose if we have a benzene dicarboxylic acid. If we have a benzene dicarboxylic acid and if we want to esterify only one of the COH group, so this can be done by converting this dicarboxylic acid into its anhydride, and then further reaction can be done. Okay, so only this can be done. So we will convert it into its derivative, that is the anhydride. So these are certain ways by which the chemoselectivity can be done. Now let's come to the use of this chemoselectivity in disconnection approach. So for this we have certain guidelines. So let's see guideline number 1. Now let's see guideline number 1. What this guideline number 1 tells. So guideline number 1, it tells that suppose if there are two different functional group, then out of two functional group, the reactive functional group will get reacted, and the more reactive will get reacted and less reactive will remain as such. So when, what we can write, when two functional groups are present, when two different functional groups, not identical, when two different functional groups are present, then reactive functional group will get reacted. Or we can say then more reactive functional group will get reacted and less reactive will remain as such, and less reactive will remain as such. For example, let's see for example some example. Suppose I take a target molecule . This is our target molecule, and and its name is cyclomethicene. Okay. Now if we disconnect it, suppose I disconnect it, then the disconnection can be done one of the way. This is one of the path. This is one of the way that we can disconnect it, or another way that we can disconnect it from here also to get the simpler starting material. So what should be the starting synthetic equivalent? The synthetic equivalent will be so no doubt this will have the minus charge here and this will have the positive charge. So here H can be added and here OH minus can be added. So I can write the synthetic equivalent. This will be the one of the synthetic equivalent, and other synthetic equivalent, this OH, and this will be the next. Okay. Now this can further be disconnected. So this can further be disconnected to get a good starting material. So here we have disconnected CO bond. Similarly here we are disconnecting CO bond. So we are getting okay plus so this will be the synthetic equivalent for this. Suppose here it has the minus charge, then it will have the positive charge. At positive charge I have attached this bromide, and here at this I have attached the H plus. So these are the simpler starting material that we are getting. Now if we write the synthesis of this, then we will see the use of this guideline in the synthesis. So let's see the synthesis. So suppose if we have para-hydroxybenzoic acid. Now this para-hydroxybenzoic acid that should be reacted with this is cyclohexyl bromide. So it has to be reacted with this. Now first of all, this in presence of alkaline medium, or in presence of suppose base, in presence of some base. So this base will abstract out, it can abstract out the proton from here or from here. So what it will give? It will give you here phenoxide ion, and here you will get a carboxylate ion. Okay, here you will get the carboxylate ion. Now this will react with a cyclohexyl bromide. Now so out of these two, here this phenoxide ion and carboxylate ion both will act as a nucleophile. So which is the more reactive nucleophile here? Either this one or this one. Now, so this is the more reactive nucleophile. This phenoxide ion act as a more stronger nucleophile in comparison to this carboxylate ion, because here you can see this is resonance stabilized. So this is resonance stabilized. That's why this will act as a reactive part in this case. So you can see here this will bromine will leave out, and you will get this part. You will get your this material. So okay. Now this can further be it can now further be reacted with this reactant to get the target molecule. Now you are getting the target molecule. So where you will see the chemoselectivity, we have seen the chemoselectivity here. We have seen the chemoselectivity here, where the more reactive functional group will get react and less reactive functional group remain unreacted. Okay, so let's see. So this is the example number 1. Now let's see the another example. Let's see the disconnection of another example. Now suppose I have paracetamol. So this is the paracetamol. If you will see the disconnection of this, then this paracetamol target molecule, it can be disconnected. It may be disconnected from here. It may be disconnected from here. And so it will have this part will have the negative charge, this part will have the positive charge, and if we write the synthetic equivalent, then the synthetic equivalent that we can write is OH here, NH minus, we can add H plus here to get the NH2 plus. To this positive species we can add Cl minus, or better to add the OCO CH3. OCO CH3. So this is the acetic anhydride. So this can also be added. This negative group can also be added over here. Okay, so this is your acetic anhydride. This is acetic anhydride. We can write it in a short form. We can write it like this. Now this can further be disconnected. Now this can further be disconnected because this NH2 group cannot easily be introduced. That's why we can do the FGI, and this NH2 can be converted into NO2. Okay, this will be converted into NO2, and by reduction, if we see the reverse reaction, then NO2 can be converted into this amine group in presence of by hydrogenation in presence of palladium. Okay, so now this can be disconnected. Now this can be disconnected, and we can write the more simpler starting material OH and plus this. Okay, so or we can, if NO2 was the NO2 plus, this will have the positive charge and this will have the negative charge. So NO2 synthon is converted into HNO3, where this here we will add the H plus to get the phenol. Now, so where now for the chemoselectivity, so where the chemoselectivity is used, the chemoselectivity that would be used here. So if I write the synthesis part, then you can see the synthesis. First of all, we have the phenol. Now this phenol is undergo nitration in presence of nitrating mixture to give you para-aminophenol. Okay. And we may also get the orthoaminophenol. Orthoaminophenol may be separated, and we need here the para-aminophenol because this OH is ortho and para-directing. So that's why it will give two products, either this one of this para-aminophenol or orthoaminophenol, and this can be isolated. Now further this will undergo hydrogenation in presence of palladium catalyst. So it will undergo reduction. It will undergo reduction into this NH2 group. And now if you will see here, two functional groups are there. One is OH and another is the NH2. So out of these two, this nitrogen being the less electronegative and oxygen being the more electronegative, that's why this NH2 will act as a strong nucleophile, OH will act as a weaker nucleophile, or we can say that this is your more reactive functional group. This is more reactive and this will be less reactive functional group. Less reactive, and according to guideline, the more reactive functional group will react and less reactive functional group will remain unreacted. So now in presence of acetic anhydride, so this part will leave out and we will get the target molecule. Okay. So this is guideline number 1. So let me rub it. Now let's come to the guideline number 2. So what this guideline number 2 tells? Now suppose in guideline number 1, say if we want here, what this guideline number 1 says, that the more reactive functional group will react and less reactive will remain unreacted. Now suppose if we want to react a less reactive functional group, then what we can do? If we want to react a less reactive functional group, then in that case the more reactive functional group that should be converted, that can be converted into another form, or that can be protected. So this is one of the note for this guideline 1. Note 1. Suppose if we want to react less reactive functional group, okay, then what we can do? Then we have to protect the more reactive functional group. Then more reactive functional group should be protected. Okay. So let's take the example for this. Now suppose we have a glycine. This is a glycine. And if you will see, then in glycine, 2 functional groups are present. One is the amine and that is the carboxylic acid. So in these 2, which is more reactive? Suppose this is more reactive and this is less reactive. And suppose if we want to react a less reactive functional group, suppose less reactive functional group should have to be reacted, means we want the reaction from C side, not the N side. Then in that case, what I have written, then more reactive functional group that should be protected. So this should be protected. If I protect this functional group, then the reaction will occur from this side. Okay, so we can protect this. The N side can be protected. And it can be protected by using, benzyloxy carbonyl chloride. So this is benzyloxy carbonyl chloride. Okay, so it can be protected by using this. Carbonyl chloride. So we will see the protection, this protecting group. In the protecting group chemistry, we will see much more about this. Okay, so now this NH2 group will get reacted with this protecting group, protecting reagent. So what we can write? Okay. Now, so this is being protected, this NH has been protected, Now the reaction can be done from C side. So now you can see this is free for the reaction. This part is free for the reaction. This is free for the reaction. Now we can do the reaction from this side. Okay, so this is the complete guideline number 1. So first of all, the more reactive functional group will react. Now if we want to react the less reactive functional group, then the more reactive side that should be protected, and this is the one of the example. Now let's see the guideline number 2. Let's see the guideline number 2. Now what this guideline number 2 tells? Okay, so this guideline number 2 tells that suppose if when one functional group reacts twice, suppose if one functional group is there and if it is reacting 2 times, then such a reaction is only possible if the product is less reactive than the starting material. Okay, what I told you, if one functional group reacts twice, then such reaction is only possible if the product formed is less reactive than the starting material. So let me write first, then I will explain you. So if one functional group reacts twice, okay, then the reaction is only possible when the product is less reactive than the starting material. Okay. Now let's see one of the example. Now suppose, let's see the disconnection of this benzyloxy carbonyl chloride. So I am taking the disconnection of this benzyloxy carbonyl chloride. Now if this is disconnected, suppose if we do the disconnection of this, then I may disconnect it from here. Okay, so this CO bond is disconnected, and the synthetic equivalent that I can write, that would be benzyl alcohol and plus. So it will have this will have the negative charge, this will have the positive charge. At negative I have added H plus, and at positive I may add the Cl minus. So I may add the Cl. Okay, so this is your phosgene. This is phosgene. Now if I write the synthesis, then you will see the use of this guideline in synthesis part. So I am writing the synthesis. So if I write the synthesis, then suppose this is your target. This is the molecule. This is the molecule, reactant molecule, having one functional group. This is the reactant molecule having one functional group. So this will get reacted with your phosgene. So no doubt this will act as a nucleophile and it will attack over here. This will attack, and minus HCl will get removed, and we will get a we are getting this target molecule. We are getting, suppose this is the target molecule. Now, so according to the guideline, if one functional group reacts twice, suppose this is the molecule, this is the target molecule. Now this molecule can again react with the benzyl alcohol, whether the reaction will occur with benzyl alcohol or not. Okay, because we have another leaving group here, and this may attack again. This oxygen may attack again over here, this electrophilic center, and this chlorine may leave out. Now, whether this will again react with this benzyl alcohol or not. So this will not react. Why? Because this is less reactive. This is less reactive. The product formed is less reactive than the starting material. This is the starting material. Which is more reactive. So if the product formed is less reactive than the starting material, then in that case, all the functional group react only once. So if the functional group reacts twice, then the reaction is only possible. The reaction is only possible when the product is less reactive than the starting material. Okay, so here, why this is less reactive? Why this is less reactive? Because if you will see, then here the resonance may occur, and this makes the electrophilic center. This makes this electrophilic weaker electrophilic center. So that's why the further reaction will not occur with the benzyl alcohol. Okay, so this is our guideline number 2. Now suppose if the product formed is, suppose if we need a product which is more reactive, suppose the product is more reactive, then the further reaction, the further unwanted reaction can be blocked, and by using some protecting groups. Okay, so suppose if a more reactive product is formed, and if we need that product, okay, then in that case the further reaction with, suppose with any starting material, that can be blocked by using the some protecting group. So let's see one of the example for this. So note for this guideline number 2. Now note for this guideline number 2. So suppose if the product formed is more reactive, suppose the product formed is more reactive, if the product formed is more reactive than the starting material. Then the further unwanted reaction can be blocked by using protecting group or protecting agent. Okay. Now let's see the example of this. So I am rubbing this guideline. Okay. Now let's see one of the general example. I am taking one of the general example. Suppose we have the hydrogen sulfide. Now this hydrogen sulfide, this in presence of base. This base can extract out one of the hydrogen from here. and so we will get a sorry, I'm writing, we will get a nucleophile, and this may attack at a alkyl bromide, and we may get RSH, that is thiol. We may get a thiol. Now, as this thiol can undergo further reaction because this is more reactive. Now, this is very reactive. So, in presence of base again, so it may react with a base to form a R, this nucleophile RS minus, and again it can react with alkyl bromide, and this will leave out to give you RS. Now suppose if we want a thiol as a product, then, and we don't need a further reaction. If we don't need a further reaction, we need a product thiol, then what we can do? Then in that case, then that can be, then protection has to be done. Then protection has to be done so that it don't react further. So the thiol can, let us see how we can get a thiol. So thiol can be prepared by the preparation of this thiol. Let's see the preparation of this thiol by another method. So preparation of thiol by thiourea method. Thiourea method. Let's see this one. Okay. So how we can get a thiol? Only thiol. We don't want this further product. So we have to protect it so that the unwanted product can be blocked. So in this method, so if we have a thiourea, so this thiourea is in presence of alkyl bromide. This will get a thiouranium salt. It will give a thiouranium salt. Now this can be hydrolyzed. So in the basic hydrolysis can be done, and we will get a urea here plus this RSH. Now we can get the thiol in this way. Okay, so this is one of the method by which we can get the thiol. So for this we have used the thiourea method. So let's see the use of this one in one of the example. I am taking one of the example. Now suppose I am taking the example of suppose if we have this target molecule that is called as a captodiamine. Okay. Now if this is our target molecule and if we want to disconnect it, so let's see the use of this guideline in this target molecule. So if we disconnect this target molecule, then we may disconnect it. And let's use here, we can disconnect it. No doubt this CS bond that can be disconnected. So I am disconnecting it from here. Okay, so this will have the minus charge, this will have the plus charge. So after disconnection, we will get the synthetic equivalent. So these are the two synthetic equivalents. These are the two synthetic equivalents. Now, so if you see, then here, suppose this is the RSH. Suppose this is your R group and this is SH. So suppose this is a thiol. This is thiol that we have to prepare. This is the thiol we have to prepare. So that's why, so we will use this guideline here. By thiourea method, this can be prepared. So by thiourea method, so that's why I will do the FGI using this guideline here. So how this can be prepared? This can be prepared by using this thiourea and this alkyl halide. It will react with giving thioureum salt, then it will give you the thiol. So first of all, what we can do that in reverse reaction. In reverse reaction, if you will see the reverse reaction, then I can write here, I can write pH, and here I can write it your, this can be converted into this Cl, okay, and this further it can be converted into this. Now this RBr, now this is R, say this is Br, I'm writing it Br. Okay, so this can be converted. So this is your RBr, alkyl bromide type of molecule. Suppose this is the R part. So this is the R part, this is Br. So this can be, this react with the thiourea and it will give you the thioureum salt. So here FGI is done. So first of all, or otherwise we can write it, this in presence of thiourea, if you do the reverse reaction, then I can write here, and then further on hydrolysis, we will get. So if we do the reverse reaction, then this first it will react with thiourea, and further hydrolysis it will give you the thiol. So like this, the thiol can be further used. So we have the more, if we have a more reactive product, then the more reactive product that can be protected. So this is the example where the protection has been done. Now further, this can be further converted into, suppose we can convert it into the OH, and OH can be converted into the bromide. So I can write OH, and now further we can do the FGI. So here I have done the FGI, and OH can be converted into bromine in presence of and this, suppose a PBr5, it can be converted, and again I may convert it into the carbonyl also. So to get the simpler starting material, pH, this is carbonyl. So carbonyl on oxidation, that will give you the alcohol, okay, and this on in presence of again PBr5, it will give you this one, and then further reaction will give you this reactant. And so by Friedel-Crafts, again we can do the FGI by Friedel-Crafts acylation. We can get S butyl plus okay. So the Friedel-Crafts alkylation of this will be done, and this will be added at the para position, and we can do. And further, this may further be disconnected. So space is problem. If space, so suppose I am writing here, again it may be disconnected from here. It may be, sorry, it can be disconnected. It can be disconnected from here, and I can write butyl bromide plus benzene thiol. So this. So now further backward reaction can be done to get this captodiamine. So we have used the guideline here at this particular place. We have used the guideline. Okay, so if you see the backward reaction, then first of all, the reaction between this benzene thiol and this butyl bromide will occur to give this one, and this can, in presence of Friedel-Crafts reaction will occur. This will get acylated at the para position, and further it will get oxidized. Carbonyl will be converted into this alcohol, and further, and in presence of PCl5 we will get this molecule, and another in presence of this thiourea, and further hydrolysis, basic hydrolysis, we will get this thiol type of molecule, and again this can be reacted with this to get the target molecule. So hope you will be able to write the synthesis. Okay, so let me write the synthesis. Okay, so I am writing the synthesis also. So if I write the synthesis of this, then first of all, let me write the synthesis. So first of all, we have benzene thiol, this in presence of butyl bromide, so we will get this molecule. Okay, now this will undergo Friedel-Crafts acylation. This will undergo Friedel-Crafts acylation in presence of AlCl3. So it will get acylated at the para position. So para position will get acylated, and further this will react with further oxidation of this, and this would be now in presence of phosphorus pentabromide. In place of OH we may get bromide. Now this may be regarded as a alkyl bromide. This may be regarded as a alkyl bromide, and now this can be reacted with this thiourea. This can be reacted with thiourea. Okay, and we may get okay, and further hydrolysis, and now so we have got this molecule, this in presence of okay, and we will get this molecule. Target molecule. Okay, so this is the synthesis part. Now so this was the guideline number 2. Now let's see the next guideline, and let me write this guideline number 3. Now if there are two identical functional groups, and we want to react only one functional group. Okay, if two identical functional groups are there and if we want to react only one functional group, then this is only possible if the product formed is less reactive than the starting material. So this is possible, then this is possible only when the product formed is less reactive than the starting material. Starting material. Okay, so let's see the example. Let's understand it with the help of example. Suppose if we have two identical functional group and we have taken the metadinitrobenzene. So if this is your target molecule, metadinitrobenzene, and if you can see two identical functional groups are present. And if you want to react any one functional group, suppose if you want to reduce any one functional group, then this is only possible when the product formed, then the first product formed is less reactive than the starting material. So for this we need for reacting only one NO2 group, we need one of the chemoselective reagent. So suppose I react it with a sodium hydrogen sulfide. Then using this is one of the chemoselective reducing agent. This is chemoselective reducing agent. Okay, so this can be written. So only one of the NO2 will get reduced to amine and another will remain unreacted. Okay, and if we further reaction is not possible, further reaction with sodium hydrogen sulfide is not possible. Why not possible? Further reaction will not occur. The further reaction will not occur. Why not occur? Because the product formed is less reactive than the starting material. This is a product which is formed is less reactive than the starting material. This is more reactive. So here this hydrogen, sodium hydrogen sulfide. Sodium hydrogen sulfide is a electron donor, we can say. Okay, and this electron donor. So it will, and this is these are the two nitro group. These are the two nitro group, and these are the electron withdrawing group. Okay, these are the two electron withdrawing group. Okay, so it will withdraw the electron and this will accept the electron. It will accept the electron. So here, but in place of NO2, now we have a electron releasing group. So this is your electron releasing group. So now we have electron releasing group here. That's why this cannot be reduced further with sodium hydrogen sulfide. So by using this chemoselective reagent, this is nitro group is first converted into amine, and this amine is now the electron releasing group. That's why it cannot be reduced with sodium hydrogen sulfide. Okay, so now we can see the use of this guideline in the further one of the example. So let's see one of the example. I am taking one of the example. Okay. Suppose we have this target molecule and this is one of the die. This is one of the die. Okay, so this is one of the die. Now if you will disconnect it, then we can disconnect it from here. We can do the disconnection from here. We can do the disconnection from here. From 3. So suppose I disconnect it further. First we can disconnect it from here, because if we have a naphthol, this naphthol part, and if we do the sulfonation, then it will, and the sulfonate, this group will go at this position. So what we can write? We can write OH and plus this, we can do H2SO4. So this will undergo sulfonation and we will get this in a reverse reaction. Now this can further be disconnected. I can disconnect it from here, and what we can do, we can get a, we can CN disconnection, and we can naphthol plus diazonium salt. So this on diazotization, this can give you this. Okay, so here we can write it diazotization. Okay. Now again this can further be disconnected. And to give you, or it may be disconnected, yes. So now we can do the FGI, and that will be converted into, first into NH2 and then into NO2. Suppose I write NH2 and then this NO2, and further FGI, and we can write it NO2 and here NO2. So if you will see, then where this guideline is used. So if we do the FGI of this, FGI means here how we can, if you see the reverse reaction, this metadienitrobenzene, this in presence of sodium hydrogen sulfide, we will get this NH2 group, only one of the NO2 will get reacted. So here in this disconnection example, we have followed this guideline. Okay, so here, or we can write this in backward. Here we have used the chemoselective reagent. So this in presence of sodium hydrogen sulfide, the backward reaction will occur, and further this you can get this target molecule. So if I write the synthesis, so let me write the synthesis of this. So if I write the synthesis, then, so first of all we have a metadienitrobenzene. In presence of sodium hydrogen sulfide. Only one functional group will get reduced, being this is a chemoselective reagent, and this amine, this in presence of NaNO2 HCl, it would be converted into diazonium salt, and further in presence of naphthol. So now this will attack over this position. If I write Okay, so here this can react over here, and further we will get this in presence of further reaction or sulfonation, in presence of H2SO4, we will get a target molecule. So this is the synthesis. So where we have used this chemoselectivity concept here. So according to this guideline, if two identical functional groups are there, and if we want to react one of them, then we can take only one equivalent of reagent in place of two equivalent of reagent. So let's understood with the help of example. First I am writing, if two identical functional groups are present, two identical functional groups are present, and we want to react only one functional group. If we want to react only one functional group, then we can use only one equivalent of reagent. In place of two equivalent of reagent, we can use one equivalent of reagent. So for this, one of the condition is this. So this is only possible when the two groups are separated by a sufficient distance. So this is only possible when two groups are sufficiently separated with each other. So let's understood this guideline with the help of example. So I am taking a target molecule having a two identical functional group. So let's take the example of this propane diol. Now if this is the propane diol, two identical groups are present and they are separated sufficiently. Suppose if we are taking the ethane diol, then the separation is not enough. So here the separation is enough. So in this case, out of these two groups, we can react only one functional group. Okay, so suppose if we have sodium here act as a base, and in presence of xylene, so it will abstract one of this hydrogen, and we will get here O minus. So it will act as a nucleophile, and it can react with any alkyl chloride, alkyl iodide. So and here, so one of the functional group is converted into the ether. One of the functional group is converted into ether. Okay. So this is the one of the guidelines. Now similarly, suppose I am taking another example. If I am taking another example where the two groups are not the identical. So this is the example where two groups are not identical. So here both the groups are identical. Here two groups are not identical because here we have the ethyl group, here we have the methyl group. So these are the non-identical groups. Non-identical groups. Okay. So in this case, if we do the reaction with alkyl halide and this base, suppose I am writing sodium and then this suppose alkyl halide, then this reaction will not occur. Means it will not give such product. You will not give such product. So this product we cannot get. Yeah, we will not get this product. So this reaction is not possible. Why? The groups are not the identical one. Okay, though they are separated, but they are not identical ones. So this rules only apply for the these two identical groups, and one of the condition that it should be sufficiently separated. If you want to react one functional group, then the two groups should be sufficiently separated with each other. Okay, now similarly, I may take another example. Suppose this is two carboxylic groups are present in this case. Okay, if two carboxylic groups are present, or suppose two OH group over here. Now, suppose this is the example. And if we want to react one functional group out of these two, if we want to react one functional group, then it will not react. Why? Because this is also not the identical one. This is not the identical. So non-identical functional group is there. So non-identical groups. That's why we will not get the product that we want. With such type of product, in this case we will not get. Suppose here sodium and second is alkyl halide is there. So this is the fourth guideline. Now let's see next guideline, and next guideline is very much related to this guideline. And this guideline, next guideline, it says that this can be done if two identical functional groups are there, and if we want to react one functional group, then this can be done by converting the your reactant molecule or target molecule into its derivative. So if we convert the reactant molecule or target molecule into its derivative, then we may change one of the functional group out of two. So if two functional groups are there, then one functional group can be converted into other functional group. If we convert the target molecule into its derivative. So I may write the guideline number 5. So this guideline number 5, it tells that if two identical functional groups are present, and if we want to react only one functional group, then we can do this by converting the reactant molecule into its derivative. Okay, we can convert this into its derivative. For example, if we have this is suppose dicarboxylic acid. Now if we want to react, two COH groups are there. If we want to react only one COH group, then we can convert this into its derivative. So by heating it, that can be converted into anhydride. So this has been converted into its anhydride, and now we can convert one functional group. So if this is reacted with, suppose if this is reacted with methanol, then this nucleophile, it can attack over this electrophilic center, and it will come back, and this will leak out. So what the product we can get? We can get the product so this is the product. So we can see that one of the functional group has been converted into the other. So by changing this into its derivative. So these are the certain guidelines which we use for the disconnection of the target molecule, or this is the chemoselective concept which we use for the disconnection of target molecule. Okay, thank you.